So this is lecture 10, and I want to discuss today section 5.2, which is second order constant coefficient linear homogeneous equations. So you remember that the general linear second order equation that's homogeneous is of the form y double prime plus p of x y prime plus q of x y equals 0, where p of x and q of x, the coefficients of y prime and y, are continuous on some open interval from a to b, which could be finite or infinite in length. And such an equation has a unique solution. So for all x naught in the interval from a to b, that is x naught is a number strictly between a and b, and for all numbers k naught and k1, there exists a unique solution y of the equation. Right? That's the equation that satisfies the initial condition that y at x naught equals k naught and y prime of x naught equals k1. Now, it's not always easy to find a solution, but there's one very important case when it is easy. And that is the case when the equation has constant coefficients. And constant coefficients means p of x and q of x are constants. Sometimes, slightly more generally, the equation with constant coefficients is written a y double prime plus by prime plus cy equals 0, where a, b, and c are numbers, constants, and it's only second order if a is non-zero. So a is non-zero, so you have a second order homogeneous equation. And if a is non-zero, you could divide by it. So it would be in this form with constants for like p and q. So the lesson today is to learn how to solve every second order homogeneous linear differential equation with constant coefficients. So, and in fact, a, b, and c are constants. So this will always have a unique solution on the whole interval from minus infinity to plus infinity. So you don't have to restrict yourself to some finite interval. The solutions will go from minus infinity to plus infinity. And the simplest idea is to try a solution of the form y is some exponential function e to the rx. All right. So what does it mean for e to the rx to be a solution of this differential equation? Or what condition would have to be satisfied? If y is e to the rx, y prime is r e to the rx, and y double prime is r squared e to the rx. So the question is there some number r such that this function solves this differential equation? If you plug this into the equation, you get a r squared e to the rx plus b r to the erx plus c e to the rx has to be 0. All right. All right, so this is the most important step in this whole lesson. Here's our differential equation, second order, constant coefficients. You look for a solution that's an exponential function, e to the Rx. It may not exist, not necessarily, but that's like a simple thing to try, and we want to know, when does such a thing work? Well, it works if this equation is satisfied. You can factor out an e to the Rx. You get AR squared plus BR plus C equals 0. And if that's the case, well, e to the Rx is never 0, right? An exponential function is never 0. So that means R has to solve AR squared plus BR plus C equals 0. So this is just an ordinary quadratic equation. Which is called the characteristic equation for this problem. So if R solves this equation, then you have a solution of the differential equation. But we know how to solve a quadratic equation. R is equal to minus B plus or minus the square root, B squared minus 4AC over 2A. And that's always the solution of this equation. It might be complex, it might be real. And depending on this discriminant, B squared minus 4AC, you really have 3 different cases. So if B squared minus 4AC is positive, we have 2 real solutions, right? Plus or minus. If B squared minus 4AC equals 0, there's only one real number that solves this, minus B over 2A. And if B squared minus 4AC is negative, we have 2 complex solutions. Right? Now, you may not know complex numbers, though. It makes sense to learn them. And we're not going to really use them. We'll circumvent that in a way you'll see in a few minutes. But this quadratic equation, every quadratic equation, if you look for the solutions, they fall into 3 classes depending on whether this discriminant, B squared minus 4AC, is positive, 0, or negative. If it's positive, you have 2 real roots for this equation. If it's 0, you have 1 real root. And if it's negative, you have 2 complex roots, 2 complex numbers that solve that equation. And we're going to consider these 3 cases separately. Okay. Any questions at this point? Okay, so we'll start with an example. Again, let me just summarize. AX squared, sorry, not AX squared. A y double prime plus by prime plus cy equals 0 has a solution y equals e to the Rx if AR squared plus BR plus C is 0. So if R solves this quadratic equation, e to the Rx is a solution. So suppose we have y double prime plus 6y prime plus 5y equals 0. So in this case, the coefficient y double prime, A, is equal to 1. The coefficient of y prime, B, is equal to 6. The coefficient of y, which is C, is equal to 5. So my characteristic equation, my quadratic equation, is R squared plus 6R plus 5 equals 0. And this is easy to solve. This actually factors into R plus 2, R plus 3 equals 0. So we have 2 solutions, R equal minus 2 and r equal to -3. Oops, I'm sorry, is that right? Nope. Let me solve this correctly. I interchanged the 5 and the 6 in my head, so let me do it right. This factors into r plus 1, r plus 5 equals 0. Then you get r squared plus 6r plus 5. So the two roots are -1 and -5. So the functions y1 equal e to the minus x and y2 equal e to the minus 5x are solutions of this ordinary differential equation. And so any linear combination. Oh, okay. So these are solutions. Are these a fundamental set of solutions? If you look at y2 over y1, that's e to the minus 5x over e to the minus x, that's e to the minus 4x. That is not constant. So by the theorem in section 5.1, two solutions of any linear second order equation form a fundamental system if and only if the ratio is not a constant. So every solution, or the general solution, of the equation is y equals some constant times e to the minus x plus some constant times e to the minus 5x. So if we start with this particular constant coefficient equation, every solution is a linear combination of e to the minus x and e to the minus 5x. And if you have an initial value problem, you can always find constant C1 and C2 that satisfy your initial values. So suppose, for example, you wanted to find the solution. You have this initial value problem. Find a solution where at x equals 0, y of 0 is 3, and y at y prime at 0 is -1. So that means you want to find, let's see, what is y of 0? So y of 0 is c1 e to the 0 plus c2 e to the 0. That's c1 plus c2, and that has to equal 3. And what's y prime of 0? If you differentiate y, you get minus c1 e to the minus x, so you get minus c1 e to the 0. If you differentiate e to the minus 5x, you get minus 5c2 e to the 0. So that's minus c1 minus 5c2, and that has to equal -1. So we have to solve two equations and two unknowns. If you add, you would get minus 4c2 equals 2. So c2 is -0.5. And so c1 will be 3 minus c2, which is 3 plus 1/2, which is 7/2. So to satisfy this initial condition, y is equal to 7/2 e to the minus x minus 1/2 e to the minus 5x. Okay. Any questions about this? Let me do another example. Let's take one from the homework. Y double prime plus 8y prime plus 7y equals 0. So let's see, the characteristic equation is the quadratic equation r squared plus 8r plus 7 equals 0. This factors into r plus 1, r plus 7 equals 0. So the solutions are r equal -1 and -7. So e to the minus x and e to the minus 7x are solutions, and every solution is some linear combination of these two. Right? That's all there is to it. We just found the general solution to this differential equation. So this is the case of a differential equation with constant coefficients, where the characteristic equation, that quadratic equation, has two distinct roots. Right? Let's look at a different case. Suppose we have the following problem. Say y double prime plus 6y prime plus 9y equals 0. Right? So here we have a differential equation for which the characteristic equation is r squared plus 6r plus 9 equals 0. And you know this factors into r plus 3 squared equals 0. Or if you look at, for this equation, b squared minus 4ac, that's 6 squared minus 4 times ac, 1 times 9, 36 minus 36, that's equal to 0. So when you have the discriminant equal to 0, your quadratic equation, the characteristic equation, is a perfect square. It doesn't have two roots, it just has one root. So the only root is r equal to -3, right? When r is -3, you get 0. So if you take the function y1 equal to -3x, this is one solution. But we know that to find the general solution, you need two linearly independent solutions. So we have to find another solution. And we know that other solution, the second solution, cannot be of the form e to the rx with r different from -3. The only exponential e to the rx that satisfies this equation is an r that satisfies the quadratic, and that r is -3. So this, as an experiment, or by repeating sort of the idea that worked in the situation in the past, suppose we let y be some function u times y1. That is, we let y equal u times e to the -3x. And can we find a function u such that u e to the -3x solves this equation? So let's try to do that. So if we differentiate, y prime is u prime y1 plus u y1 prime, or u prime e to the -3x. The derivative of e to the -3x is -3 e to the -3x. That's y prime. What is y double prime? It's u double prime e to the -3x minus 3u prime e to the -3x. If I differentiate this, I get another -3u prime e to the minus 3x, and minus 3 times minus 3 plus 9u e to the minus 3x. So y double prime is u double prime e to the minus 3x minus 6u prime e to the minus 3x plus 9u e to the minus 3x. Or if I like, I can factor out e to the minus 3x. Times u double prime minus 6u prime plus 9u. So I have y double prime plus 6y prime plus 9y equals 0. That's the equation we want to solve. One solution is y1 equal e to the minus 3x. And I look for a second solution, y, which is of the form u e to the minus 3x. And if y is u e to the minus 3x, y prime, I just calculated it. I can factor out e to the minus 3x. It's e to the minus 3x, u prime minus 3u. And y double prime is e to the minus 3x, u double prime minus 6u prime plus 9u. So if I take this and plug them into the differential equation, y double prime plus 6y prime plus 9y, that's going to equal e to the minus 3x, u double prime minus 6u prime plus 9u, plus 6y prime, 6e to the minus 3x, u prime minus 3u, plus 9y, 9u e to the minus 3x. I can factor e to the minus 3x out of all of that. I get u double prime minus 6u prime plus 9u plus 6u prime minus 18u plus 9u. That's e to the minus 3x. Let's see, I have minus 6u prime and plus 6u prime, so they cancel. I have 9u plus 9u, that's 18u minus 18u. They cancel. So I just get e to the minus 3x u double prime. And that has to equal 0. The exponential, again, is never 0, so this happens if and only if u double prime is 0. And the only function whose second derivative is 0 is a linear function, c1 plus c2x. So if I let y equal c1 plus c2x times e to the minus 3x, that's c1 e to the minus 3x plus c2x e to the minus 3x, I get a solution of this differential equation. And y1 equal e to the minus 3x and y2 equal x e to the minus 3x. These are two solutions which form a fundamental system of solutions for this differential equation. Suppose again we wanted to solve the initial value problem with y of 0 equal 3 and y prime of 0 equal minus 1. So c1y1 plus c2y2, this is c1 e to the minus 3x plus C2 e to the plus C2 y1 prime, sorry, y2 is x e to the minus 3x. And C1 y1 prime plus C2 y2 prime. If I differentiate y1, I get minus 3C1 e to the minus 3x. And if I differentiate y2, I get e to the minus 3x minus 3x e to the minus 3x. So at x equals 0, this gives me C1 plus 0, and that's supposed to equal 3. So C1 is equal to 3. And at x equals 0, this gives me minus 3C1 plus, when x is 0, plus C2 equals minus 1. So C2 is 3C1 minus 1, which is 3 times 3 minus 1, that's 8. So for this initial condition, the general solution is y equals 3 e to the minus 3x plus 8x e to the minus 3x. So this gives me the solution to the initial value problem. So this is the case when the discriminant b squared minus 4ac is 0. So the quadratic equation has one solution r, and the two solutions that make up a fundamental system are e to the rx and x e to the rx. At least in this case. And if we want to see whether this is true in general, the general proof goes through just the way we solve this particular case. So we have ay double prime plus by prime plus cy equals 0, and b squared minus 4ac equals 0. All right, so this is the case we're considering. And if you look at the ax squared plus ar squared plus br plus c equals 0, the characteristic equation r is equal to just minus b over 2a. There's only one solution. Or just to follow, let me say, solution of this equation is R1 equals minus B over 2A. This equation becomes so one solution of this equation is Y1 equals e to this, let me just write R1x, where this is the R1. And we want to look for another solution, Y2, of the form u equals e to the R1x for some u. And just as we did before, we differentiate Y2, we get Y2 prime is u prime e to the R1x plus R1 u e to the R1x. Y2 double prime is u double prime e to the R1x plus R1 u prime e to the R1x plus, when we differentiate this, we get R1 u prime e to the R1x. That gives me this, so I get two of these. Plus, when I differentiate this with e to the R1x, I get R1 squared u e to the r1x. So this is equal to e to the r1x times u double prime plus 2r1 u prime plus r1 squared u. And I want to know what is the function u such that y2 equal to u e to the e to the r1x solves this equation. So just plug everything into the equation. I get a times the second derivative plus b times the first derivative. If I factor out e to the r1x, I get u prime plus r1u plus c y1 e to the r1x plus cy plus c u e to the r1x. And I have an e to the r1x in each term, which I can factor out. So I get e to the r1x times a u double prime plus 2a r1 u prime plus a r1 squared u plus b u prime plus b r1 u plus cu. Which is equal to e to the r1x a u double prime plus I have two terms that involve a u prime, 2a r1 plus b times u prime. And then I have three terms that involve u plus a r1 squared plus b r1 plus c times u. But r1 was a solution of this quadratic equation. So this is equal to 0. And r1 is also minus b over 2a. So 2a r1 equals minus b, or b plus 2a r1 is 0. So this is also 0. So we get this is simply equal to a u double prime e to the r1x, and that's equal to 0. A is non-zero because we have a second order equation. So u double prime has to be 0. So u has to be c1 plus c2x again, a linear expression. And so again, we get that y, which is u e to the r1x, is c1 plus c2x e to the r1x, or c1 e to the r1x plus c2x e to the r1x. Okay. So this gives us an extremely simple rule to solve every second order constant coefficient equation for which the characteristic equation has only one root. Let's look at another example. Let me take one from the exercises at the end. Suppose we have the equation y double prime minus 4y prime plus 4y equals 0. We want to find all solutions of this equation, the general solution. So the characteristic equation is r squared minus 4r plus 4, which you recognize immediately as r minus 2 squared equals 0. So the only solution is r equal to 2. So the general solutions of this equation, a pair of fundamental solutions, is y1 equals e to the 2x, and y2 is equal to x e to the 2x. So the general solution is y is c1 e to the 2x plus c2x e to the 2x. That's the general solution. Let's check. If this is equal to y, y prime is 2c1 e to the 2x plus c2 e to the 2x plus 2c2 x e to the 2x. Y double prime is equal to 4c1 e to the 2x plus 2c2, oops, I hope this is right, plus 2c2 e to the 2x plus 2c2 e to the 2x plus 4c2 x e to the 2x, and 2 plus 2 is 4, so that just makes this a 4. So y double prime minus 4y prime plus 4y is equal to this. I can factor e to the 2x out of this. I get 4c1 plus 4c2 plus 4c2x minus 4y prime so I multiply this by minus 4, and I can factor out an e to the 2x. So minus 8c1 minus 4c2 minus 8c2x plus 4y, 4 times this, that's plus 4c1 plus 4c2x. What do I get? I have, hope I made a mistake somewhere. Let's see. I have 4c2 minus 4c2. They cancel. I have 4c1 plus 4c1, that's 8c1, minus 8c1, so they cancel. 4c2x plus 4c2x is 8c2x minus 8c2x, so they cancel. So this is 0, and it checks. This works. Okay. So you now know how to solve the second order constant coefficient equation in the case 2 when the discriminant is 0. Okay. So let's look at the third case and the last case. So we have the differential equation a dot y double prime plus by prime plus cy equals 0. The characteristic equation is ar squared plus br plus c equals 0. And the general solution is r is equal to minus b plus or minus the square root of b squared minus 4ac over 2. And in this case, b squared minus 4ac is negative, right? This is case 3. The discriminant is negative. Now, what this means is if b squared minus 4ac is negative, the equation has solutions, but they are complex numbers, right? What do you do? Well, let's start again with an example. So a nice example, which is 5.2.3 in the text, is y double prime plus 4y prime plus 13y equals 0. So the characteristic equation is r squared plus 4r plus 13 equals 0. So r is minus 4 plus or minus the square root of b squared minus 4ac minus 52 over 2 let's see, 52 minus 16 is minus 36. So R is equal to minus 4 plus or minus 6, square root of 36 is 1, square root of minus 1 over 2, which is minus 2 plus or minus 3, square root of minus 1, that's just what we call I. So the two solutions of this equation, there are two solutions, but they're complex numbers. R1 is minus 2 plus 3I, and R2 is minus 2 minus 3I. And this suggests that if it made sense to us, I mean, it makes perfect sense in mathematics, but maybe you haven't gotten to the point in mathematics where you've learned about complex exponentials. You would have y1 equals e to the minus 2 plus 3i x, and y2 is e to the minus 2 minus 3i times x. It's just that in the prerequisites for this class, you haven't been required to learn about e to a complex power in the exponent. I mean, you could think if you had the usual rule for exponents, this is e to the minus 2x, e to the 3ix, and this is e to the minus 2x, e to the minus 3ix. And this suggests maybe we should look for a solution of the form y equal e to the minus 2x times some function u. So let's try that and see what happens. So just to repeat, we have the differential equation y double prime plus 4y prime plus 13y equals 0. And we look for a solution of the form y equals u e to the minus 2x for some function u. And then y prime is u prime e to the minus 2x minus 2u e to the minus 2x. And y double prime is u double prime e to the minus 2x minus 2u prime e to the minus 2x minus 2u prime e to the minus 2x plus 4u e to the minus 2x. So this is u double prime e to the minus 2x minus 4u prime e to the minus 2x plus 4u e to the minus 2x. And just to make it slightly less cumbersome, I can factor out e to the minus 2x, u double prime minus 4u prime plus 4u. So this is y prime. And again, I can also factor out e to the minus 2x from this. I get that. And this is what, so y prime, and y double prime. So y double prime plus 4y prime plus 13y equals y double prime e to the 2x times u double prime minus 4u prime plus 4u plus 4y prime, so factor out e to the minus 2x, plus 4 times u prime minus 2u, plus 13y, that's 13u e to the minus 2x. Let me just simplify the algebra. This is e to the 2x, u double prime minus 4u prime plus 4u, plus 4u prime minus 8u plus 13u. That's e to the 2x minus 4u prime plus 4u prime cancel. I have 4u plus 13u, that's 17u, minus 8u, that's 9u. So I get u double prime plus 9u equals 0. Now, so u must satisfy, because this is not 0, it's an exponential, u double prime plus 9u equals 0. And solutions of this equation are cosine of 3x and sine 3x, so any linear combination of them. Right? Because if you take the cosine or the sine, you differentiate twice, you get minus 9 times what you started with. So you get a solution of this. So the general solution of this differential equation is y equals u times e to the minus 2x. That's e to the minus 2x times c1 cosine 3x plus c2 sine 3x. And this is typical of what happens whenever you have a constant coefficient equation where the discriminant is negative. Your solution will be of the form an exponential times the cosine and an exponential times the sine. Right? So that always, always happens. So let's look at now the general solution of the equation with a negative discriminant. So we have ay double prime plus by prime plus cy equals 0. And b squared minus 4ac is negative. So remember, we're looking at ar squared plus br plus c equals 0. The solution is r equals minus b plus or minus the square root of b squared minus 4ac over 2a. If b squared minus 4ac is negative, I can write this as minus b plus or minus the square root of. So if b squared minus 4ac is negative, if you multiply by minus 1, 4ac minus b squared is positive. So I can write this as minus 4ac minus b squared over 2a. So r is equal to minus b plus or minus the square root of this positive number, 4ac minus b squared, times the square root of minus 1i over 2a. Which is equal to minus b over 2a plus or minus the square root of 4ac minus b squared over 2a times I. And to follow the notation in the text, suppose we let lambda be minus b over 2a and omega to be the square root of 4ac minus b squared over 2a. So the roots of my equation are R1 equals lambda plus omega I omega, and R2 is lambda minus I omega. So for this choice of values of lambda and omega, which are written down in the book, and you can look them up whenever you need to know them, these are solutions of the characteristic equation. And what I want to do is to look for solutions of the form y equals some function u times e to the lambda x. This is my lambda. And I want to find u. So let me just summarize this again, and then we'll continue. I have ay double prime plus by prime plus c equals 0. And b squared minus 4ac is negative. So 4ac minus b squared is positive. It has a square root because it's positive. And the roots of the equation ar squared plus br plus c equals 0 are r equals minus b over 2a plus or minus square root of 4ac minus b squared over 2ai, and I'm calling this lambda. And I look for a solution of the form y equals u e to the lambda x. So if that's y prime is u e to the lambda x plus lambda u e to the lambda x, which is e to the lambda x times, sorry, this is u prime plus lambda u. And the second derivative, I differentiate this again, I get u double prime e to the lambda x plus lambda u prime e to the lambda x plus lambda u prime e to the lambda x plus lambda squared u e to the lambda x, which is e to the lambda x times u double prime plus 2 lambda u prime plus lambda squared u. So ay double prime plus by prime plus c y is equal to e to the lambda x times a times this, a u double prime plus 2 a lambda u prime plus a lambda squared u plus by prime, so I get plus bu prime plus b lambda u plus cy plus c u. That's e to the lambda x times what? I have a u double prime, I have u prime, I have 2a lambda plus b u prime plus a lambda squared plus b lambda plus c times u. And lambda is minus b over 2a. So 2a lambda plus b is 0. So this term disappears. And a lambda squared plus b lambda plus c, let's see, how does that simplify for me? Let me just compute this. I'm curious to see. So A lambda squared plus B lambda plus C. Lambda is minus B over 2A. So that's A over B squared over 4A squared plus B times lambda minus B squared over 2A plus C. So this is AB squared over 4. So this is B squared over 4A minus B squared over 2A plus C is minus B squared over 4A plus C. That's equal to 4AC minus B squared over 4A. 4AC minus B squared is omega squared over 4A. I just want to check this algebra because let me just start it again because that's easier. So again, we have the differential equation, AY double prime plus BY prime plus CY equals 0. The characteristic equation is AR squared plus BR plus C equals 0. So the solution is minus B plus or minus square root of B squared minus 4AC over 2A. And we're in the case where B squared minus 4AC is negative, which if we multiply by minus 1 is the same as saying 4AC minus B squared is positive. So R, the roots of this characteristic equation, are minus B plus or minus the square root of 4AC minus B squared minus sign in front over 2A, which is minus B over 2A plus or minus the square root of 4AC minus B squared over 2A times I. And I'm going to write this as lambda plus or minus omega I. So lambda is minus B over 2A, and omega is the square root of 4AC minus B squared over 2A. And I'm going to look for a solution of the form y equals u times e to the lambda x. This is my lambda. So then y double prime is u prime e to the lambda x plus lambda u e to the lambda x, which is e to the lambda x times u prime plus lambda u. And y double prime is e to the lambda x times lambda u prime plus lambda u plus e to the lambda x times the derivative of this, u double prime plus lambda u prime. So if I put this together, I get e to the lambda x times lambda times u double prime, lambda u prime plus another lambda u prime, 2 lambda u prime, plus lambda u. So if I take these three expressions for y prime, and yw prime, and put them into my differential equation, I get ay double prime plus by prime plus cy equals a times this, and factor out e to the lambda x from every term, a times this, that's au double prime plus 2a lambda u prime plus a lambda u plus by prime plus bu prime plus b lambda u plus cy, which is plus cu. So this is equal to e to the lambda x au double prime plus 2a lambda plus b u prime plus a lambda plus a lambda u plus b lambda u plus c u. Okay. Let me just see what, there should be a lambda squared here somewhere. So when I differentiated y prime, I get lambda e to the lambda x. Yeah, so it's e to the lambda x u double prime plus lambda u prime plus lambda u prime plus lambda squared u. That's better. Squared. So a lambda squared plus b lambda plus c times u. Okay. So this is e to the lambda x times a u double prime, a lambda squared plus b lambda plus c what is that? U double prime plus 2 lambda u prime plus lambda squared u prime plus lambda u, and u. So this is exactly correct. This is all supposed to equal 0. So I can drop the e to the lambda x. And this is 0. So what I get is a u double prime plus a lambda squared plus b lambda plus c times u equals 0. And omega is equal to the square root of 4ac minus b squared over 2a. So omega squared is 4ac minus b squared over 4a squared. And actually, let me just look at this. A lambda squared plus b lambda plus c, lambda is minus b over 2a. So lambda squared is b squared over 4a squared. So this is equal to a times b squared over 4a squared plus b times lambda minus b over 2a plus c. So this is b squared over 4a minus b squared over 4a plus c. So this is minus b squared over 4a plus c, which is 4ac minus b squared over 4a. Aha, excellent. So this is a times 4ac minus b squared over 4a squared. This is equal to a omega squared. So this differential equation was a u double prime plus a omega squared equals 0, or divide out by the a, u double prime plus omega squared equals 0. So u is a solution of this differential equation. And this differential equation, oops, sorry, there's a u here. The solution of this differential equation is u equal to C1 cosine omega x plus C2 sine of omega x. Good. So this proves the rule, and it's the rule that you have to remember. AY double prime plus BY prime plus CY equals 0. You let lambda be minus B over 2A. You let omega be the square root of 4AC minus B squared over 2A. So this is the case when B squared minus 4AC is negative. And the general solution is e to the lambda x C1 cosine omega x plus C2 sine of omega x. So that is the last step in this whole process. And let's look at an equation, an example. This is problem number 5 in the homework. Y double prime plus 2y prime plus 10y equals 0. So the characteristic equation is r squared plus 2r plus 10 equals 0. In this case, b squared minus 4ac is 2 squared minus 4 times 1 times 10 is 4 minus 40 is minus 36, which is negative. So again, in this equation, a is 1, b is 2, c is 10. Lambda is minus b over 2a is minus 2 over 2 is minus 1. Omega is the square root of 4ac minus b squared over 2a. 4ac minus b squared is 36 over 2. 6 over 2 is 3. So for this differential equation, the general solution is y equals C1, so is e to the minus x, lambda is minus 1, C1 cosine 3x plus C2 sine 3x. And let's just check. So if I take this to be y, y prime is minus e to the minus x, C1 cosine 3x plus C2 sine 3x plus e to the minus x times minus 3c1 sine 3x plus 3c2 cosine 3x. That's equal to e to the minus x times what? I have cosine 3x times 3c2 minus c1 plus 3c2 cosine 3x. And I have sine 3x times what? C minus c2 minus 3c1. So y double prime is e to the minus 3, e to the minus x minus this c1 minus 3c2 cosine 3x plus c2 plus 3c1 sine 3x plus e to the minus x times the derivative of this. The derivative of this is minus 3 times this, so it's 3c1 minus 9c2 sine 3x, and 3 times this, so it's minus 3c2 plus 9c1 cosine 3x. So that's y prime, and y double prime. So if I take y double prime plus 2y prime plus 10y, that's e to the minus x times this. So I have something times the cosine of 3x. For y double prime, it's c minus 3c2 minus 3c2 minus 9c1. If this is correct, hard to believe it is, sorry, minus 3c2 minus 9c1. That looks like minus 8 cosine 3x. And for the sine 3x, I have, sorry, c1 minus 3c2 minus 3c2. C1, so I have minus 8c1 minus 3 minus 6c2. And the coefficient of sine 3x is this plus this. So that's minus, so that's 6c1 minus 8c2 times sine 3x plus 2y prime. This is y prime, so this is minus 2c2 plus 6c2 cosine 3x minus 2 minus 6c1 plus 2c2 sine 3x plus 10y, which is 10c1 cosine 3x plus 10c2 sine 3x. So if I look up, let's see, what do I get? I get for cosine 3x minus 6t2 plus 6c2. These cancel. Minus 8 minus 2 plus 10. These cancel, so this just gives me 0 here. And here I have 6c1 minus 6c1 minus 8 minus 2 minus 10 plus 2. Well, lo and behold, everything cancel, and this gives me 0. Okay, excellent. So this is the whole theory of constant coefficient, second order homogeneous linear differential equations. We can now solve them all. And there's some homework. I said it was due today, but I should make it due at the end of the week because it involves problems from this section. And this is as far as the first midterm exam will cover. So you will remember that that exam is on Wednesday, October 19th. Yeah. So in about a week and a half. We have 2 classes before that, some of part of which I will spend on review, but this is as far as that first midterm goes. So you should keep that in mind and take advantage of the fact that we have a break of almost a week and a half to the next class. And I will assign some more homework problems. And the more you do, the better. Okay. Any questions about this? This is probably the easiest topic for the rest of the course because we have a complete method for solving all such linear equations with constant coefficients. And that is, that doesn't always happen. Okay. Any questions before we quit for the morning? If not, then be well, everyone. And next class is a week from Wednesday. Bye all.